Oké, take 2. Hey, we doen meteen het tweede filmpje. So this is also about energy. It's something we did cover in class, but since I figured that a lot of you are struggling with this and a lot of people were already ill or not at school the week before the lock or like when the school officially closed, I do want to make this a movie as well, just to help you out. So this chapter is about energy. You probably got that by now, but so what you need to know is that we're doing a lot of calculations in energy. So you'll figure that out as we go along. As a startup, so most energy actually, so from at home, it comes from electricity or gas. Electricity you probably know because most of your appliances that you probably use use electricity, but maybe not every kid knows is that we also use a lot of gas. So we use gas to cook. That's actually when you can actually see it. But more often not, we also use gas to heat up our house. And as you can see, about half of the energy used at home is actually just used to heat up your house. So that's quite a significant amount of energy. This is technically possible to do with electricity, but it's not very common yet. So most of the gases in the Netherlands is heated by gas. What we did in the lesson as well is the following. So we recapped energy from chapter, I believe, about electricity at the beginning of the year. Energy is capital E, and you can either write it down in joule or in kilowatt hour. And what you need to remember is that 1 kilowatt hour resembles 3.6 million joule, or 3.6 megajoule if you want to. So we're also going to look into specific heat, and before we introduce it, it's important to know what it is. So specific heat is whenever you heat something up for only 1 degree Celsius, and in this case it's per kilogram. So if you heat a kilogram of water, for instance, you require about 4,180 joule. If you would heat something else up, like a metal, you would require far less. You may know or you may not know that metals, for instance, they transfer heat way easier, and therefore they require less heat to heat it up a certain temperature. Other substances require a lot more heat to heat it up. And the relationship with the substance and how much energy is required to heat it up is called specific heat. So the higher this number is, the more energy, the more joule it requires to heat it up 1 degree Celsius. You can find these values in your BINAS. You don't need to know them by heart. I'm not sure what the table is, but you can look it up yourself. So these values you can look up, and it's called specific heat of warmtecapaciteit in Dutch. Just that you know. And then energy efficiency. So we know that from the other video I already made, maybe you've seen that before this one, heat efficiency is whenever energy is lost to something else, and it's often heat. So for instance, this light bulb you can see that only 10% of the electrical energy that goes in, only 10% is used to actually produce light, which is the ultimate goal of a light bulb. This is because this old translucent light bulb works by heating up this wire, and because it becomes so warm, it actually starts emitting a color. But to become so hot, it also needs to produce a lot of energy. And as you can see, almost 90% of all the energy actually is lost to heat, and only 10% goes to where you want it to go. So we would say this has a very low efficiency, about 10%, or in this case exactly 10%. Newer lights, like the LED, the light emitting diodes, have way higher efficiency. So they have an efficiency in the middle of the 50%. So that means that less electrical energy is needed to produce the same amount of light, because it's more efficient. So these were the questions you have to do. You probably finished them already. If not, please work on it. Now the important stuff. So we have 2 formulas, and we're going to be using them a lot. So one is to calculate a certain amount of heat. This capital Q is just a symbol for heat, the abbreviation for heat, and it's always in joule. So you have the capital E for energy, but when we're talking specifically about warmth, about heat, we're talking about Q. What you need to know is the mass. The mass is in kilogram. Like I said, this is a specific heat value, the specific heat quantity. You can actually find in the minus is always the amount of joule you need to heat it up 1 degree of Celsius for each kilogram that you want to heat up. So if you want to heat up 400 grams, you actually only use 0.4 kilogram. We always use an initial and a final temperature. The initial temperature is the temperature at which you start at, for instance 15 degrees, 20 degrees, and you heat it up is always a higher value, 25 degrees, 50 degrees, that depends. And then there's an extra formula you need to know, that's about efficiency. And efficiency is just the amount of the amount of energy produced, how much of that goes towards the useful energy. Or if heat is produced, how much of the heat produced actually is used to, for instance, cook your potatoes, or how much of this heat is used to heat up your shower. So remember, Q is heat, E is energy. They are often the same thing, but not always, so be patient with this. What is nice to know is that you can use, if you have 1 liter water, it's exactly 1 kilogram. So often we're talking about heating up 50 liter of water, we actually mean 50 kilogram of water. And most of you people know this, but water boils at 100 degrees Celsius. So yeah, we use that a lot. So these was the homework questions, but I want to do example together. So we're doing question 15 on page 297 together. So it's about an old house. It uses an old hot water boiler. It runs a bath, and to run the bath, 0.60 m3 of a cubic meter of gas is burned. This bath contains 56 liters of water and is heated from 15 to 72 degrees Celsius. It is run 400 times a year. We might need that later. So first, how much energy is needed? So when you see this question, the first thing that needs to pop in mind is, I'm going to need this formula, because this tells me exactly how much heat is required. So we're probably going to need that. The M stands for mass, and in this case, mass we don't directly know, but we do know that there's 56 liters of water, and as you might recall, 1 liter is exactly 1 kilogram. So the mass is 56 kilogram of water. The heat capacity of water, you can find it in the book. It's also in your BINUS. Apparently it's 4,180 joule to heat up 1 kilogram for only 1 degree. So if you have 1 kilogram of water and you want to heat it up 10 degrees, you need 10 times this amount in joule. You can find it on page 295 or in your BINUS. And this is specifically the heat capacity of water. If you would use another substance, you would have a different value here. My initial temperature is very low, it's only 15 degrees Celsius, and I want to heat it up until 72. So my initial and my final temperature is 15 and 72 degrees Celsius. Now I have my mass, I have my heat capacity, and I have my initial and final temperature, so I can fill it in. Pretty straightforward at this point. Mind the brackets, please, because if you don't, you will mess up. So when you use the initial and final temperature, mind the brackets, or first calculate the delta T, the difference in temperature. And you'll find out that you need this many joules, which is about 13 megajoule, give or take. So yeah. Then question B, we want to calculate the efficiency of the boiler. So given was to run this bath, we need 13 megajoule or a little bit more to heat up this water. And apparently it uses 0.60 m3 of gas. What we need to know now is how much energy does 1 m3 of gas use. And a lot of you probably read over this, but it's in the book somewhere. It's on page 292. 1 cubic meter of gas produces 32 megajoule. And 1 megajoule is a million, so a million joule. So this is 32 million joule. We don't have 1 m3, but we have 0.6. So we need 19.2 megajoule, or 19,200,000 joule to warm the, oh, it's not the shower, by the way, it's the bath, excuse me for that. But you get the point. So this is how much joule we actually, so this is how much heat is actually produced by burning this much gas. We already know from last question how much we needed, so we can calculate efficiency using this formula. We know how much heat is actually produced. This is the total heat that is produced by burning this much gas. And from the last question, we know that the useful warmth was 13 million something, or when you're accurate using this, you can use this answer. So dividing the two by each other times 100% gives you an efficiency of somewhere above 69%. The answer book rounds in between. I'm personally not a fan. I personally like you to round at the end of the question, but all the same. So yeah, that's how you do it. I hope this helped a little bit. Again, we're having a live lesson in a couple of hours, so maybe you can ask your final questions then. Cheers!